Hi, I am Ms. Sushma, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering College, Hyderabad. In this session, we are going to discuss about the realization structures of digital filters. That is, we have different types of realization structure. In that, we are going to discuss about the direct form 1 and direct form 2 realization structures of IARE filter. So, before going to the topic, we have to know what is realization. So, here realization involves the converting a given transfer function h of z into a suitable filter structure that is generally depicted using block or flow diagrams and shows the computational procedure for implementing the digital filter. So, here in the realization structure, we will take the transfer function of the filter and our difference equation, and we will convert that into suitable block diagram or flow diagram of the filter. So here the digital filter function can be realized in the recursive or non-recursive type. So here the digital filters are two types: IARE filters and FIR filters, that is infinite impulse response filter and finite impulse response filter. So for recursive realization, the current output y of n is a function of past outputs as well as past and present inputs. It depends about the output of the recursive filter depends on the y of n, depends on the past outputs as well as the present and past inputs. So this corresponds to an infinite impulse response digital filter. So here the IARE filter output y of n depends on the past outputs, present and past inputs. So here output of the IARE filter depends on the past outputs as well as the past and present inputs. So this IARE filter is also called as the recursive filter. Okay, and for non-recursive realization, the current output sample y of n a function of only past and present inputs only. Past and present inputs only. It will not depend on the past outputs. It will depend on the only past and present inputs. This form corresponds to the finite impulse response digital filter. So here the digital filters are two types: IARE filter, infinite impulse response filter, finite impulse response filter. We can call IARE filter is a recursive filter where the output depends on the past outputs and present and past inputs, whereas FIR filter is also called as non-recursive filter. Here the output depends of the FIR filter depends on the only past and present inputs. It will not depend on the past inputs. So this is the difference between the IARE and FIR filter. Here we have to realize the transfer function of these both digital filters or difference equation of the filters in terms of block diagram. In terms of block diagram, we have to represent the transfer function and difference equation of these digital filters in terms of block diagram. Okay, or signal flow diagram. So here the main advantages of arranging sets of difference equation is to reduce the computational complexity, memory requirements and finite word length effects in computations. So the main advantages of the realization structures of the digital filters is to reduce the computational complexity, memory requirements and finite word length effects in computations. So first we will take the IARE filter difference equation here. So an infinite impulse response system is described by the difference equation y of n. So here the y of n depends on the past outputs as well as present and past inputs. Okay, we are representing general difference equation where our y of n depends on the past outputs as well as present and past inputs. By substituting k is equal 1, here we are going to get a1 y of n minus 1 and k is equal to a2 y of n minus 2 plus k is equal 3 a3 y of n minus 3. So here y of n minus 1, y of n minus 2, y of n minus 3. These are the past outputs. Okay, as well as if you observe the second term, here if you observe, substitute k is equal 0, we are going to get b naught x of n, where x of n is the present input. If you substitute k is equal 1 to m, that is if k is equal 1, b1 x of n minus 1, k is equal 2, b1 b2 x of n minus 2, and k is equal 3, b3 x of n minus 3. So these x of n minus 1, x of n minus 2, these are the past outputs. So the general difference equation for IAR filter, it depends on the past outputs, and if you substitute k is equal 0 in the second term, you will get the present input, that is b naught x of n, and from k is equal 1 to m, we are going to get the past inputs. So this is the general difference equation we are taking, and we are going to apply the Z transform for the y of n. So here the main aim is to find out the transfer function. So here we are applying the Z transform for the above equation, that is equation 1. So here if we apply the Z transform to the y of n, we are going to get the y of z is equal minus k is equal 1 to n ak y of n minus k. If we apply the Z transform to the y of n minus k, then we are going to get the z power minus k y of z. So if we apply the y of minus n minus 1, if we apply the Z transform, we are going to get the z power minus 1 y of z. For y of n minus 2, we are going to get the z power minus 2 y of z. K is equal 2 here. For y of n minus 3, z power minus 3 y of z. So like that, if you apply the Z transform to the minus sigma k is equal 1 to n ak y of n minus k, so that is we are going to get the ak z power minus k y of z plus the second term for k is equal 0 to m bk x of n minus k. If we apply Z transform, that will we are going to get z power minus k x of z. Okay. Take this term k is equal 1 to n ak power z power minus k y of z to the left side. Make the y of z terms, whatever the terms we have to make them to the left side. So y of z plus sigma k is equal 1 to n ak z power minus k y of z, and sigma k is equal 0 to m bk z power minus k into x of z. So here take the common y of z term, and we are going to get the 1 plus sigma k is equal 1 to n ak z power minus k is equal sigma k is equal 0 to m bk z power minus k x of z. So here the different general difference equation, here we are getting this one. So what is transfer function here? Transfer function h of z can be realized the output response by the input response. Okay. So here y of z by x of z. So here y of z by x of z is equal sigma k is equal 0 to m bk z power minus k by 1 plus this term. 1 plus sigma k is equal 1 to n ak z power minus k. This is the transfer function of the general transfer function of the IAR filter. Okay. So from that we are getting the transfer function of a linear time invariant digital filter can be expressed as a transfer function in the z domain, that is h of z is, we can write that as sigma k is equal 0 to m bk z power minus k by 1 plus sigma k is equal 1 to n ak z power minus k, and expand these terms by substituting k values. Here in the numerator, if we substitute k is equal 0, we are going to get here b naught z power 0 plus, if we substitute k is equal 1, we are going to get b1 z power minus 1, b2 z power minus 3, 2 plus b3 z power minus 3 up to this will be the limit up to m. So last term is m bm z power minus m. Divided the denominator, we also expand the k values, and by substituting k is equal 1, we are going to get a1 z power minus 1 plus a2 z power minus 2 plus a3 z power a plus last limit is up to n. So an z power minus n. So we are expanding the sigma values, that is we are substituting k values in the numerator and denominator, we are going to get this equation. So this is the form for recursive filter which typically leads to an infinite impulse response behavior. So here we have the poles, we have the zeros system and pole system. So this is the form of realization form of a transfer function for the recursive filter, that is IARE filter. So if the denominator is made to equal to unity, whatever the denominator term, we have numerator and denominator for the recursive filter. If we made the denominator term made equal to the unity, then that is no feedback. Then this becomes the finite impulse response filter. So that is nothing but non-recursive filter. So if the denominator is equal to 1, then the real transfer function is equal to the FIR filter transfer function. So there is no feedback for the FIR filter, because the output will not depend on the past outputs for the FIR filter. So when the causality assumed, a LTI filter can be uniquely characterized with its transfer function h of z. Already we discussed about, we derived the transfer function of the LTI filter here. And if k is equal to, here 1 plus k is equal 1 to n ak z power minus k, we can write this as sigma k is equal 0 to n ak z power minus 1. So if k is equal 0, a power 0, z power 0. So a naught plus sigma k is equal 1 to n ak z power minus k. So this a naught we are going to take that as 1. Okay. So the difference equation, this is the transfer function of the LTI filter we are going to get here, and the transfer function, if we consider the transfer function, we can write that the output depends on the past outputs as well as present and past inputs. Okay. So here the basic elements we are using here is, for y of n minus 1, y of n minus 2 are x of n minus 1 and x of n minus 2 up to x of n minus m. So we are going to shift the input and output by some units. So we are going to use here the delay elements. So here to get the y of n to y of n minus 1, we have to apply one delay unit for that one. So y of n to y of n minus 1. Okay. So to get the y of n minus k, we have to apply z power minus k delay types, k times delay the output, we are going to get the y of n minus k. Okay. And this sigma means we have to use the adders and the scalar multiplier for the bk into x of n minus k. So the general difference equation, if we want to realize in terms of block diagram, our transfer function or difference equation, to realize that in terms of a block diagram, the basic elements we are going to use is delay elements, multipliers and adders. So computing y of n involves, so y of n minus 1, y of n minus 2 up to y of n minus n, that are past outputs as well as present input and past inputs. So to get the past outputs and past inputs, we have to use the delay elements, and for scalar multipliers for the ak into y of n minus k or bk into x of n minus k. So we have to use scalar multiplier here, and we have to use adders for this sigma. Okay. So the basic elements we are going to use for the realization of the digital filters are delay elements, multipliers and adders. So if take the adder, we are taking the two inputs x of n and y of n. If we want to use the adder in terms of block diagram, we can represent that by using this symbol. Okay, I am giving the x of n input and another input is y of n. So if we want to add this x of n and y of n inputs, then we have to use in the block diagram by using this symbol. So here we are going to get x of n plus y of n. Okay, and multiplier, here we are using the scalar multiplier for here. So x of n is multiplied with the alpha, some constant, either it may be a naught, a1, a2, a3 or b naught, b1, b2, b3. So the general constant I am taking is alpha. So here x of n is multiplied by the alpha. We can represent that just that by arrow mark r like that. Okay. So here alpha is multiplied with x of n, that we can be write as alpha into x of n. So we can refer this also x of n alpha into x of n. Okay. Another representation we will use in the block diagram is delay element. So here for unit delay, x of n is equal z inverse x of n minus 1. So if we want to delay by k units, so z power minus k, that is x of n minus k. We can delay by k units represented by the z power minus k. Then x of n is given to the z power minus k, then x of n minus k. So here we can represent that as x of z is given to the one delay unit. We can write that as z inverse x of z. We can write that one. Okay, these both are equal. So the basic representation of the block diagram, we will use adders, scalar multipliers and delay elements. So the basic symbols we are going to use these three in the block diagram representation of digital filter. So for example, draw the block diagram and signal flow graph representation of LTI system whose input x of n and output y of n satisfy the following difference equations. So here y of n, we are taking minus a1 y of n minus 1 minus a2 y of n minus 2 plus b naught x of n. So it is depending on the past outputs and present input. Okay. So here first we have to represent that in terms of block diagram. So first take input and the scalar multiplier for the input is b naught x of n. So this we are multiplying the x of n by the b naught. So here we are going to get the b naught x of n. And what are the another terms we are going to get here? Y of n minus 1 and y of n minus 2. So further, we have to take the y of n here, and to get the y of n minus 1, we have to give that to the one delay unit. So that is represented in terms of block diagram by z inverse. So here z power minus 1 is given to the y of n. We are going to get the y of n minus 1. And for y of n minus 1, the scalar multiplier factor is minus a1. So that we are going to represent here minus a1. So here we are going to get minus a1 y of n minus 1. Okay. Another term is minus a2 y of n minus 2. So to get the y of n minus 2, we have to give to the one delay element to the y of n minus 1. So that's why we are giving to the z power minus 1, that is one delay element. So y of n minus 1 will become y of n minus 2, and the scalar multiplier is minus a2 here. So that will be represented by just arrow mark and minus a2. So here we are going to get the minus a2 y of n minus 2. So here the term is added with the minus a1 y of n minus 1, and these two will be added here. So total b naught x of n plus minus a1 y of n minus 1 is added here, minus a2 y of n minus 2. So total output is equal to the b naught x of n minus a1 y of n minus 1 minus a2 y of n minus 2. So this is the basic block diagram or signal flow graph representation of LTI system. Here just we are using the delay elements and scalar multipliers and adders. So the basic blocks we are using for the block diagram representations are adders, that will be represented by the symbol, and multiplier, scalar multiplier alpha into x of n, and delay element by the z power minus 1. So here x of n is given, you are going to get the x of n minus 1. So this is basic example for the block diagram representation of a difference equation. Okay, if you want to represent y of n is equal 0.7 x of n plus 0.3 x of n minus 1. See, I am taking here x of n and here y of n. So here x of n is first scalar factor is 0.7. So here it is we are going to get is 0.7 x of n plus we have only present and past input. So here we are another term we are going to get is 0.3 x of n minus 1. So x of n minus 1 is given to the one delay element, here we are going to get the x of n minus 1, and further the scalar multiplier is the 0.3. Okay, so here we are going to get 0.3 x of n minus 1, and this will be given to the adder. So here one term is 0.7 x of n and another term is 0.3 x of n minus, these two will be added and that will be equal to the y of n, that is 0.7 x of n is one term and another term is 0.3 x of n minus 1. This is the block diagram representation for the given equation. Another example, here y of n, he is depending on the past output, present input, past output and present input and past output. Okay, so for the first we are taking x of n. Okay, what are the x of in terms here, x of n and x of n minus 1. So x of n, the scalar multiplier is 0.8, so 0.8. Then we are going to get here x of n is multiplied with 0.8, we are going to get a 0.8 x of n. Another term is x of n minus 1. So from x of n, we are going to give x of n to the one delay element. So here we are going to get x of n minus 1. Okay. Next, the scalar multiplier for the x of n minus 1 is 0.4. And this is given to the adder. So here only we have two terms, x of n, that is 0.8 x of n is coming from here. And another term is 0.4 x of n minus 1. Okay, this 2 is added. So we got this 0.8 x of n plus 0.4 x of n minus 1. Another term is 0.5 y of n minus 1. So here from it is depending on the past output. So y of n. So the feedback that is coming from y of n. And to get the y of n minus 1, we are giving to the one delay element. So that is we are going to get y of n minus 1. And scalar multiplier for that one is 0.5. And this is given to the here. So this term is added with the, here we are going to get 0.8 x of n plus 0.4 x of n minus 1 is added with the product. Here we are getting 0.5 y of n minus 1. This will be added here, 0.5 y of n minus 1 is equal to y of n. Okay. So this is the block diagram representation of the difference equation. So here first we have the two types of filter. Realization, here we are going to discuss about the realization of IARE filter and FIR filter. So first we will discuss the realization of IARE filter. So we have different methods. In this session we are going to discuss about the direct form 1 structure and direct form 2 structure only. So here IARE systems whose impulse response is infinite length of samples. So that system impulse, IARE system impulse response length is in the range of infinite length. So here the different types of structures for realizing IARE systems are direct form 1 structure, direct form 2 structure, cascade form structure, parallel form structure, transposed form and lattice structure and ladder structure. Okay. So here we are going to discuss about the, in this session, direct form 1 structure and direct form 2 structure. In direct form 1 structure, first before going to discuss about the direct form 1 structures, here we are taking the general difference equation of the IARE filter, transfer function of the IARE filter. So here that I can write the h1 of z into h2 of z, that is h1 of z is sigma k is equal 0 to m bk z power minus k plus into h2 of z is 1 by sigma 1 plus sigma k is equal 1 to n ak z power minus 1. So we have numerator and denominator. We are taking separate transfer function for that h1 of z and h2 of z. So here h1 of z is a all zero system and h2 of z is a all pole system. Okay, numerator is a all zero system and denominator is a all pole system here. So here input x of n, we are taking input x of n, and first in the direct form 1 we will realize the all zero system is followed by the all pole system. So the numerator part will be realized first, then it is followed by the all pole system, that is h2 of z. then that is y of n. So this realization is in the direct form 1. First we will realize the numerator, that is all zero system, is followed by the all pole system, that is denominator. In this will be equal to the input if we are given the x of n, all pole system, that is denominator is the realized first in terms of block diagram, and it is followed by the all zero system, that is h1 of z. Then we are going to get output. This is in direct form 2. The basic difference for direct form 1 and direct form 2 is, in the direct form 1, just we will realize the all zero system first, and it is followed by the all pole system. In direct form 2, we will realize the transfer function of h of z in all pole system first, and it is followed by the all zero system. Okay. So first we will discuss how to realize the infinite impulse response system transfer function into direct form 1 structure. Okay. So first we will take the IARE filter difference equation. Already we know, see, IARE filter the output depends on the past outputs and present and past inputs. So past outputs, if you substitute k is equal 1 to n, you will get the y of n minus 1, n minus 2 up to n minus n past outputs. If you substitute k is equal 0, here x of n, b naught x of n, present input. And if we substitute k is equal 1 to m, so b1 x of n minus 1, x of n minus 2 up to x of n minus m, those are the past inputs. So just we are taking the IARE filter difference equation and expand that y of n difference equation by substituting k values. So k is equal 1, a1 y of n minus 1, k is equal to a2 y of n minus 2, a3 y of n minus 3, up to, if you up to 1 to n. So the last term is a n y of n minus n. In the second term, if you substitute here k is equal 0, we are going to get b naught x of n, present input, 1 to m, b1 x of n minus 1, b2 x of n minus plus bm up to bm x of n minus m. So these we are expanding the difference equation by substituting k values and apply z transform to the y of n. So here we are going to get y of z. So already we discussed, if we apply z transform to the y of n minus k, we are going to get the z power minus k y of z. Okay, so y of n minus 1, substitute k is equal 1, z power minus 1, y of z. For y of n minus 2, z power minus 2, y of z. For example, x of n minus 1, z power minus 1, x of z. So just we have to remember for this z transform, we have to apply z transform here. Y of z is equal minus a1 z power minus 1 y of z. For minus a2 y of n minus 2, we will write as minus a2 z power minus 2 y of z, a3 y of n minus 3, a3 z power minus 3 y of z. Like that we have to apply the z transform to the expanded difference equation. And we here, whatever the input terms are there, we are taking that as w of z, or in the difference equation w of n. Okay, so here we are taking the whatever the input terms, we are considering them as w of n in the difference equation or w of z in the z transform the difference equation. So here w of z is equal sigma k is equal 0 to m bk z power minus k x of z. So here these are the whatever the input terms are there, we are considering that as w of z. Okay, in the difference equation is w of n, that is b naught x of n plus b1 x of n minus 1 plus up to bm x of n minus m. Okay, so here then y of z will become, y of z is equal whatever the past outputs plus w of n. So past outputs are a1 minus a1 z power minus 1 y of z minus a2 z power minus 2 y of z up to y of plus y of z w of z, and the difference equation same, these two we are representing in terms of y of z, in y of n it will be minus a1 y of n minus 1 minus a2 y of n minus 2 plus w of n. So w of n will be the input terms, present and past inputs. Okay. So we have to take this difference equation or transfer function, we have to represent in terms of direct form 1 by using the delay elements, scalar multipliers and adders. So here first I am going to take the W of n, and I'm going to represent the W of n in terms of block diagram, because here W of n is all zero system. Okay, and y of n is first it will be taken as all zero system followed by the all pole system. Then we are going to get y of n. So first I am going to take the all zero system, that is input terms. So here I am taking x of n. I want to realize this w of n here. Okay, w of n depends on the b naught x of n, b1 x of n minus 1, bm x of n minus m up to. Okay, so x of n. So here I want to get the w of n output. So x of n, the first term is b naught x of n. So first it is multiplied by the b naught, and we are going to get here term is b naught x of n. And the second term is b1 x of n minus 1. So for that x, to get the x of n minus 1, I am giving that to the one delay element. So here I am going to get the x of n minus 1. Okay. And the scalar multiplier is b1 here. The quotient for that one is b1. So it is multiplied by the b1. So here I am going to get the b1 x of n minus 1. Okay. This is added here. And the second term is b2 x of n minus 2. So to get the x of n minus 2, I am giving x of n minus 1 to the one delay element to get the x of n minus 2 here. So here we are going to get the x of n minus 2, that is the quotient for that is b2. So here we are going to get b2 x of n minus 2. Then this will be added here. Like that, the input terms b3 x of n minus 3 up to bm, that is z power minus 1, bm, the quotient for that is bm. So here we are going to get bm x of n minus m. So it will be like that, every term will be added here. So this is x of n term, we are from w of n from the present and past inputs. So here the y of n will depends on past outputs as well as w of n. So here w of n is directly added to the y of n, and the y of n has the minus a1 y of n minus 1. So from the y of n, we are going to get the y of n minus 1 by giving the one delay element. So here we are going to get the y of n minus 1. And the quotient for y of n minus 1 is minus a1. So for that we are going to use the scalar multiplier. The quotient is here minus a1. So here this will be added here. And the second term is minus a2 y of n minus 2. So for that, give to the one delay element for the y of n minus 1. We are going to get the y of n minus 2. And the quotient for the y of n minus 2 is minus a2. We are using scalar multiplier. By arrow mark, we have to represent that quotient minus a2, and it is given to the one adder. So here the term we are going to get is minus a2 y of n minus 2. Here minus a1 y of n minus 1. Here we have wn. Like that, if the last term for this one is am an y of n minus n. So here last z power minus 1, the quotient is minus an. This term will be added here. So here these past outputs are added with the w of n. So we are going to get the y of n. So this is the basic difference equation representation in terms of direct form 1 structure. If we consider the transfer function of this IARE filter, that will be h of z will be written as b0 plus b1 z power minus 1 plus b2 z power minus 2 up to b m z power minus m by 1 plus a1 z power minus 1 plus a2 z power minus 2 plus a3 z power minus 3 up to an z power minus n. So for this one, if you want to, if they give the transfer function of the filter, directly we can represent here the numerator is all zero system. So that will be in the left hand side. The numerator is the all pole system, that will be in the right hand side. So first the B0, B1, B2, Bm are the coefficients for the x of n minus 1, x of n minus 2, x of n minus 3. So whatever the coefficients we have, directly we have to take B0, B1, B2, B3 and 1 delay element here. Okay. For mth order system, m delays we will get here. M delays units and m adders. Okay. For denominator, the term is 1. So here it is 1 and A1, A2, A3 up to an z power minus n. In terms of transfer function, we are here. So whatever the coefficients are there, the opposite sign we have to write here. Minus A1, minus A2, minus A3. The arrow mark, if we observe the loop, this will be in the anti-clockwise direction. This is in the clockwise direction. Okay, because the y of n depends on the past inputs. Here it has a feedback from the y of n. So here y of n minus 1, y of n minus 2, y of n minus 3. So it is a IARE filter. Our IARE filter output depends on the past outputs, present input as well as past inputs. Okay, this is a general representation of direct IARE filter difference equation and transfer function in terms of direct form 1 structure. So this is the direct form 1 structure for the IARE filter difference equation or transfer function. So here we have B0, B1, B2, B3, Bm up to Bm. These are the coefficients for the x of n minus 1, x of n minus 2, x of n minus 3, and we are using the delay elements and A1, A2, A3. This is the all zero system numerator. All zero system, that is sigma k is equal 0 to m B0 x of n minus k. So this is all zero system and this is all pole system. Right hand side is all pole system, that is 1 plus sigma k is equal 1 to n y of n minus k. Okay, this is direct from 1 structure. Here we are going to use the m plus n plus 1 multiplication, where m is the order of the numerator and n is the order of the denominator, and m plus n additions, and we are using the m plus n memory locations for the direct form 1 structure. So here the order of the system is m and the order of the system for the pole system is n. So for that we are going to use the m plus n plus 1 multiplications and m plus n additions and m plus n memory locations we are going to use in the direct form 1 structure. Then the limitations of direct form 1 structure. First, this form is practical for only small filters but may be inefficient and impractical for complex designs. It is applicable for only small order filters, that is small filters. In general, this form requires 2n delay elements for a filter of order n. If the filter of the order is n and we are going to use 2n delay elements in the direct form 1 representation. Okay. So since the number of delay elements used in the direct form 1 is more than the order of the difference equation, it is not effective. Okay, here we are using the more number of delay elements than the order of the filter. It lacks the hardware flexibility because we are using the more number of delay elements here. And there are chances of instability due to quantization noise. Here we are going to get the quantization noise. There are chances of instability due to the quantization noise. These are the disadvantages of direct form 1. So to reduce the number of delay elements from the direct form 1 to direct form 2. So here in the direct form 2, we are going to reduce the number of delay elements. So first of all, we are going to see one example for the direct form 1 structure. Then we will discuss the direct form 2 realization structure. Okay, here obtain the direct form 1 realization of the LTI governed by the equation. So here they given the one difference equation y of n. Okay, so here it has the past outputs as well present inputs and past inputs. So we are taking difference equation and we are applying the Z transform here. Z transform to the above equation. So here we are going to get y of z is equal 13 by 12 z power minus 1 y of z minus 9 by 24 z power minus 2 y of z and minus 1 by 24 z power minus 3 y of z. X of n will become x of z and x of n minus 1 will become 4 into z power minus 1 x of z and x of n minus 2 3 into z power minus 2 x of z. Already we discussed this one. X of n minus k, if you apply z transform, this will become z power minus k into x of z. Okay, substitute k values and we can write directly here. We have to take this equation and we have to represent that in terms of block diagram representation. Okay, so here the equation for this one is, if we consider the difference equation here, y of n is equal 13 by 12 minus 13 by 12 y of n minus 1 minus 9 by 24 y of n minus 2 minus 1 by 24 y of n minus 3 plus x of n plus 4 into x of n minus 1 plus 3 into x of n minus 2. So here first we are taking x of n. Okay, x of n term is only we don't have any quotient, only x of n is there, the quotient is 1 for that. So directly it is given here. Here we are going to get x of n. And another input terms are 4 into x of n minus 1. So first to get the x of n minus 1, we are going to give the one delay element. So directly if we see, observe the z transform equation also, but directly we can write that one. So here the first term, the first input terms we are going to see here, x of n, x of z, z inverse x of z, z power minus 2, x of z. So here z power minus 1, x of z. So we are giving x, taking the x of z, we are giving to the z inverse, that is one delay element. So we are getting z inverse x of z, the quotient is 4. So we are giving to the one scalar multiplier 4 here. Here we are going to get 4 into z inverse x of z. And other term is z power minus 2 x of z. So already we have z power minus 1. So z power minus 1 and if both are cascaded, we are going to get z power minus 2. So already we have z power minus 1 is given to the another one delay element z power minus 1. So here we are going to get z power minus 2 x of z. The quotient for that is 3. So we are multiplying with the 3. So here we are going to get the 3 into z power minus 2 x of z. These two will be added here. So x of z plus 4 into z power minus 1 x of z plus 3 into z power minus 2 x of z. So this term present and past inputs we got, that is all zero system. First we realized in terms of block diagram. Then that is given to the term all pole system. So here the output y of z, from that we are giving to the one delay element z inverse. So here we are going to get z inverse y of z. The factor quotient for that is minus 13 by 12. So but that is multiplied by the minus 13 by 12. So here we are going to get minus 13 by 12 z inverse y of z. And another term is minus 9 by 24 z power minus 2 y of z. So already we have z power minus 1. We are given to the another delay element. So we are going to get z power minus 2 y of z. So here minus 9 by 24 z power minus 2 y of z. And another term is z power minus 3 y of z is the quotient is minus multiplied with the minus 1 by 24. So here we are going to get y of z. So these all will be added by using these adders, and here this term will be added here, minus 13 by 12 z power minus 1 x y of z minus 9 by 24. Another term is z power minus 2 x of z. Another term is minus 1 by 24 z power minus 3 y of z. So this is total of our y of z. So either we can take the y of z, or we can, by using the difference equation y of n also, we can realize the difference equation in terms of block diagram. So this is direct form 1 structure. So if we take the direct form 2 realization, the alternate direct form 2 only needs n delay units. The disadvantage of direct form 1 structure is here, if the order of the filter is n, in direct form 1 structure, the delay elements we are going to use is 2n delays. In direct form 2, if the order of the system is n, we are going to use the only n delay units. Okay, we are reducing the number of delay units in the direct form 2 realization. So here this structure is obtained by reversing the order of the numerator and denominator section of direct form 1. So in the direct form 1, first we will realize the all zero system, that is numerator, and then it is followed by the all pole system. Then we will get the y of n. Okay, but in direct form 2, the order of these reversing the order of the numerator and denominator section, we will get the direct form 2. So first we will realize the all pole system, that is denominator part, then it is followed by the all zero system. Then we will get the y of n. So this is the difference between the direct form and direct form 2, and we are reducing here number of delays also. So the disadvantage is that the direct form 2 increases the possibility of arithmetic overflow for the filters of high Q, that is or resonance. It has been shown that as Q increases, the round of noise of both direct form topologies increases without bounds. So here, as the Q increases, the round of noise of the both direct form increases without bounds. This is because conceptually the signal is first passed through an all pole filter before the result of that is saturated. Then it is passed through the all zero system. So that's why as Q is increases, the round of noise of the both direct form structures increases. So first we will how to realize the direct form 2 realization. Here we are taking the transfer function of the IARE filter and we are expanding that h of z by substituting k values. And here we are taking dividing this y of z by x of z into two terms. We can write this y of z by x of z as y of z by w of z and w of z by x of z. Okay, y of z by w of z and w of z by x of z. So here, this y of z by w of z, we can write that as h1 of z and this is h2 of z. Okay, so y of z by w of z, that is numerator part, that is all zero system. This is all zero system, and w of z by x of z is all pole system. All pole system. So we can taking this h1 of z, this as h2 of z. So what we discussed as direct form 2 is first realized by the all pole system and followed by the all zero system. So here w of z by x of z, we can write that as w of z is equal to x of z minus a1 z power minus 1 w of z minus a2 z power minus 2 w of z minus a n w of z. So here we have two terms here, y of z by w of z as b0 b1 z power minus 1 plus b2 z power minus 2 up to bm all zero system, and w of z by x of z we can write as that as 1 by a0 plus 1 plus a1 z power minus 1 plus a2 z power minus 2 up to an z power minus z. So cross multiply these two here. Here we are going to get w of z a1 z power minus 1 w of z plus a2 z power minus 2 w of z up to an z power minus n w of z is equal to x of z. So from this we are going to get this equation, and from that only keep w of z in the left hand side and remaining terms we have to bring to the right hand side. Then a1 z power minus 1 w of z will become x of z minus a1 z power minus 1 w of z and minus a2 z power minus 2 up to minus an z power minus w of z. And then from this equation we will get write the y of z is equal this term. Okay, so we have to realize these two equation in terms of block diagram. So first we will take the w of z. So here w of z is x of z minus a1 z power minus n w of z. So here we are, if we consider the x of z, we are taking the x of z. Okay, we have to get the w of z here. Just I am explaining how to represent equation 1 in terms of block diagram here. So minus a1 z. So first second term is a1 minus a1 z power minus 1 w of z. Okay, so here it is w of z. From w of z we are giving to the one delay element. So here we are going to get W of Z. The scalar multiplier for that is minus A1. Okay, and second term is another Z power minus 2. Here we are going to get Z power minus 2 W of Z. Like that, here we are representing these two equations in terms of block diagram. See here. Here we are going to get W of N here. Okay. W of N. Here we are going to get W of N minus 1. So here minus A1 W of N minus 1. Here W of N minus 2, 1 is given to the another delay element W of N minus 2. So here minus A2 W of N minus 2. And here it is W of N minus 3 minus A3 W of N minus 3. So this gives these all systems will functions will be added here, and then this will be added to the second all zero system. Here this is B0 plus B1 W of N minus 1 into B1 plus B2 W of N minus 2 B3 W of N minus 3, like that. So here we are going to represent these 1 and 2 equations in terms of block diagram representation here. Okay. So the common terms we have here, the delay elements Z power minus 1. We can combine these delay elements and we can make one delay element here. So here Z inverse, Z inverse, Z inverse, we are making the combining the two delay elements as one delay element, and we are reducing the number of delays by combining the delay elements from N to N to N here. So here the basic representation, if we have the transfer function of the filter is B0 plus B1 Z power minus 1 plus B2 Z power minus 2 up to Bm Z power minus m by 1 plus A1 Z power minus 1 plus A2 Z power minus 2 plus An Z power minus n. Then we can write that as, see here, the numerator part in the direct form 2, the denominator part, that is all pole system we will realize first. So here whatever the quotients we have, take that opposite sign here. So with A minus A1 minus A2 minus A3 minus M, this is in the clockwise direction. So here we are going to get this y of n, this y of n by minus A1 y of n minus 1 minus A2 y of n minus 2 minus Am minus 1 y of n minus m minus 1 minus Am y of n minus m. Okay, and another loop is here, B0 x of n plus B1 x of n minus 1 plus B2 x of n minus 2 and Bm minus 1 x of n minus m plus 1 and Bm x of n minus m. Okay, so this we have to represent the all zero system, all pole system first. This is all pole system, and we have to realize then all zero system. So in the first left hand side, whatever the quotients are there, A1, A2, An, the negative sign we have to represent for the scalar multiply from the transfer function, and numerator part all pole system, whatever the sign is there, plus or minus, keep the same, and we have to keep here B0, B1, B2, B3, Bm minus 1, Bm. So this is the direct form 2 realization, and here the number of delay elements are, the order of the new denominator is n and numerator is m. So here the maximum of m comma n delay elements we are going memory elements we are going to use here, and we are going to reduce the delay elements from 2n to n elements. Okay, so here h of n we are taking h of n and h2 of n we are cascading. This is zero system and pole system. So this is in the direct form 1 structure. So we can realize that as H2 of n, all pole system first and followed by the zero system. This is in the direct form 2 structure. Both are equal, but we are reducing the number of elements from the direct form 1 to direct form 2. So limitations of direct form 2 are it also lacks hardware flexibility. There are chances of instability due to quantization noise. So this is the disadvantage of both the filters here. So here there are the instability due to quantization as in the direct form 1 and direct form 2 structures. So here in the direct form 2 realization is the given the difference equation. So first we have to take the transfer function for this one, find out the transfer function here by applying the Z transform. So first apply the Z transform to the given equation. Y of z power minus 1 y of z minus 4 into y of z minus 4 into z power minus 3 y of z is equal to x of z plus 3 into x of z into z power minus 2. Okay, take the common y of z here. We are going to get 1 plus z power minus 1, 4 into z power minus 3, x of z is 1 plus 3 into z power minus 2. Then transfer function will be the output response by input, that is 1 plus 3 z power minus 2 by 1 plus z power minus 1 minus 4 z power minus 3. Okay, so here 1 plus 3 power z minus 2. So here this is like b0 plus b1 z power minus 1 plus b2 z power minus 2. 1 plus a1 z power minus 1 plus a2 z power minus 2 plus a3 z power minus 3. So from this transfer function we have to realize the this difference equation transfer function into block diagram. So here what is transfer function we got here is 1 plus 3 z power minus 2 by 1 plus z power minus 1 minus 4 z power minus 3. So here from the transfer function, first we have to take the x of n and y of n, and the denominator terms will be given first here. So first y of n, z inverse, the coefficient for that is 1. So here we have to take a negative quotient here, minus 1. Another term is z power minus 2 here. So that is z power minus 1, z power minus 1 here. Okay, so here from z power minus 3 we got here, that is here we are going to get the quotient is minus 4. In the denominator, whatever the quotient is, we have to take the opposite side, that is 4 here, and this will be added here. And the numerator has the 1 plus 3 power z minus 2 here. So this will be x of n will come here, and this will be given to the quotient is b1 is 3. So here we are going to get 3 into z power minus 2, 7, and here we are going to get z power minus 1 and 4 minus 4 z power minus 3. So this is the realization structure of direct form 2. So the basic differences between the direct form 1 structure and direct form 2 structure is this realization uses direct form 1 realization uses separate delays for both input and output signal samples. That is, for all pole system and all zero system, we are going to use the separate delay elements in the direct form 1 structure, whereas in direct form 2 structure, we are using the single delay elements for the all pole system and all zero system. That is, for both the input and output signals, we are going to use the single delay elements, that is memory elements. For second, for the n-1th or n-1th order IR system, direct form 1 requires m plus n-1 multipliers and m plus n-2 adders and m plus n-2 delay elements. Whereas in the direct form 1 structure, for the same order IR filter, here it uses m plus n-1 multipliers, same multipliers and same number of adders, but only we are reducing the delay elements, that is maximum of m-1 or that is order of the numerator, order of the denominator, maximum of m-1 and n-1 delays. We are reducing the number of delay elements from direct 1 structure to direct form 2 structure. And it is also called non-canonical because it requires more number of delays. So direct form 1 structure is also called as non-canonical structure, whereas direct form 2 structure is called as a canonical structure because it requires minimum number of delays. And the fourth point, it is not efficient in terms of memory requirements compared to direct form 1, direct form 2, because here we are using the number of delays are higher compared with the direct form 2 structure. So here in the direct form 2 structure, it is more efficient in terms of memory requirement compared with the direct form 1, because we are reducing the number of delay elements here. In direct form 1 can be viewed as two linear time invariant system in cascade. The first one is non-recursive and the second one is recursive filter. The first one is non-recursive because here in a direct form 1 structure, first it will be all zero system. It is all pole system. That is numerator input terms we are taking first. It realized first and it is followed by the all pole system, that is denominator output terms we are going to find. So here all pole system is here, denominator is a output depends on the past output. So here it is a recursive filter, it is a non-recursive. So the first one is non-recursive in the direct form one, the second is recursive because the second one output depends on the past outputs. In the direct form system, it is about first we will realize the all pole system, then it is all zero system followed by the all zero system. So here it is recursive and it is non-recursive structure. Okay. So the basic differences between the direct form 1 and direct form 2 realizations are discussed now. So in the next session, the remaining realization structures will be discussed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.